So, hi everyone, and good afternoon. Thank you for joining us today. It's a pleasure to introduce Professor Joseph Katz today. He is a distinguished professor of engineering and the director and co-founder of the Center for Environmental and Applied Fluid Mechanics at Johns Hopkins University. He's also a member of the National Academy of Engineering and a fellow of the American Society of Mechanical Engineers, the American Physical Society, and the American Society of Thermal and Fluids Engineering. His research extends across several fields in fluid mechanics, with a common theme involving experimental fluid mechanics and development of optical and ultrasonic diagnostic techniques. Thank you, Joe, for accepting our invitation today at this late time, and it's all yours.
Okay. First of all, thank you for inviting me. You hear me well? Do you hear me well? Okay. Thank you for inviting me. It's a very strange time for a lecture, but usually we have meetings in the middle of the night for the Australians, so you're getting even with me today. Anyway, I'm going to talk about compliant wall boundary layers, turbulent boundary layers. First of all, the person that has done most of the work is a graduate student, Yuhui Lu. I get to talk about it, and Office of Naval Research got to pay for it. And then the kind of background, the interest in compliant wall boundary layers started actually in 1950s, where there was a perception that somehow the compliant surface causes reduction of skin friction. For turbulent boundary layers, we have not managed to reduce skin friction using compliant walls. However, compliant walls are used on a regular basis as a means of suppressing noise. So since Australia is about to buy submarines, this is actually quite a relevant topic, because the idea is you coat a submarine surface with a compliant wall, and as a result of it, you reduce the excitation of the structure or separate it from the pressure fluctuations in the boundary layer, and as a result of it, presumably reduce noise. So this is the primary reason that the Navy is interested in compliant walls. There's always the dream of reducing drag, but we are not closer to it than we were in the last 50, 60 years. Now, in recent years, two things have happened. There has been renewed interest in the compliant wall boundary layers. First of all, because of the development in numerical techniques. So over the last few years, there have been two direct numerical simulations that actually the compliant wall is really being modeled as a viscoelastic surface, as opposed to springs and dampers that used to be used before. And there are two papers, like by Rosti and Brandt and by my colleague in our department, the Tamer Zaki's group, that simulated the flow around in compliant wall boundary layers, usually lower Reynolds numbers than experimental data. We started playing with it in on the order of about 8-9 years ago, and first paper published in 2017 and followed in 2020. There's another paper that published this year, where we developed techniques to measure both the three-dimensional flow and the compliant wall deformation simultaneously, and as a result of it, we're able for the first time to correlate between the flow field, the three-dimensional flow field, three-dimensional pressure field, and the compliant wall deformation. And what is the relationship between them? What is the two-way coupling? How does the compliant wall affect the boundary layer? How does the boundary layer affect the compliant wall, etc.? As kind of as a teaser, you can see on the right-hand side an example of what happens to the inner part of a boundary layer when you have a compliant wall, but the deformations are already in the order of a half wall unit to one wall unit. You already see significant differences in the flow structure in a part of the boundary layer. look on the total left side, you can see that very similar phenomena have been seen in numerical simulations in DNS. So there are several sources already that show the same kind of trends. Anyway, our objective is to investigate the interaction of high Reynolds number two-ball boundary layer with a compliant wall. The idea is to develop, and we wanted to develop and implement techniques that enable us to measure the 3D flow, pressure distribution, and obviously the surface deformation, and eventually go ahead lead. If you have the 3D pressure distribution, you can also calculate what the radiated dipole noise, and from that relate whether the deformation of the wall affects noise generation directly. Anyway, what I'm going to talk about it mostly is about flow deformation interactions and how to affect the boundary layer. And what surprised me more than anything else is when you have deformations that are well below 1 wall unit, you already cause significant changes to the flow structure in the boundary layer, something that will not happen in a rough wall. So the impact of the compliant wall is substantially more intense than that of a rough wall, and I will try to explain why that happens. Now, the experiments being conducted, I'm an experimentalist in my heart and soul. The experiments are performing refractive index matched water tunnel. We perform the 3D velocity measurements using tomographic PIV. I will show more details about it. From the three-dimensional velocity distribution, time resolved velocity distribution, we calculated the 3D pressure distribution by integrating the material acceleration. And once I have the pressure distribution, we can correlate it with simultaneous measurements of the wall deformation. And we use interferometry to measure the wall deformations because they're extremely small. As a matter of fact, when we calibrate it, we can, using interferometry, resolve deformations are in the order of, the uncertainty is in the order of 10 nanometers. We even had problems calibrating it because of the fine resolution, because there are no other techniques that are more fine, that are finer than that. And again, we try to correlate the pressure to the deformation and try to understand mechanisms. I will elaborate. First of all, the test facility, it's a water tunnel and standard shape, a test section 6 inches by 8 inches. To give you an idea, it's a recirculating tunnel. For cavitation tests, we also have a cyclone separator. For the present experiments, it is not really important. The only difference between that and a typical water tunnel is the liquid. We actually have a concentrated solution of sodium iodine in water. We use it for rough wall boundary layers where we match the refractive index of the fluid with that of the wall roughness. And as we use acrylic roughness, and as a result of it, we can perform velocity measurements between the roughness elements. But again, in the present study, is not really the most important element. The fluid, by the way, has a specific gravity of a 1.8. Refractive index is almost 1.49. So it's a fluid that is almost twice as heavy as that of water. Maximum velocity in this tunnel with water is 40 meters per second. With the sodium iodide solution, it's about 11.2 meters per second. Free stream turbulence intensity is about 0.7%. So besides that, it's a standard water tunnel. The compliant material itself, coating, was made out of PDMS, so it actually has slightly different refractive index, it's 1.4. To control the stiffness of the PDMS, we mix it with gel at different concentrations, and based on the concentration of the gel, you can get materials that has a Young modulus varying anywhere between 1 megapascal to about 50 kilopascal, depending on how much gel you mix with the dye. We mold the surface, and the bottom wall of the tunnel becomes an integral part of the system, and you end up with a compliant surface on the wall. For some of the experiments, we had a half an inch or 1.2 centimeter compliant wall. For most of the measurements that I showed today was about 5 millimeter. And the thickness of the wall plays an important role in the flow structure and behavior of the material. I will explain in a minute. Materials again vary between 158 kilopascal, the compliant wall stiffness, to somewhere in the order of 1 megapascal. Now, to measure the flow, as I mentioned you before, we use tomographic PAV. Basically, it involves, so this is top view, you can see the test section. You end up with 4 cameras looking at a thick light sheet, about 1 centimeter thick light sheet that you use to illuminate the sample volume. So that's a standard tomographic PAV. The only difference between that and a typical tomographic PAV system is that we bleed a little bit the light. So if this is one view and this is a front view, the mirror M1 has a 99.9% reflectivity, and we bleed about 0.1%, which is basically, as far as the illumination intensity of the sample volume, is basically negligible. So you generate a beam that becomes a reference beam, and the second beam, the beam that goes through the sample volume, including the compliant wall at the bottom, there is another mirror under the test section. It has a reflectivity also of 99.9%. So most of the light is reflected back to the test section, increasing the illumination intensity. But 0.1% gets transmitted and interferes with the reference beam. And the interference pattern is really the source of information that we use to determine the shape of the wall. Because as the light propagates through the compliant wall, the compliant wall has a refractive index slightly lower than that of the fluid, about 1.4. And as a result of it, you change the optical path lengths, and then you create an interference pattern. I will show you some of them. And you record the interference pattern, and you infer from them the shape of the wall. Give you an idea, a range of Reynolds numbers. Reynolds tau in the data that I'll show you varies between 3,300 to 8,900. The field of view of the Mach Zehnder interferometer was 27 by 10 millimeter. The sample volume, the tomographic PAV field of view was somewhere in the order 23 by 12 by 8 cubic millimeter, which you translated to wall units of several thousand delta nu times 1,000 times 610 in all 3 dimensions. You have some more information about the PIV resolution, etc. But basically, we use the same, the summary, we use the same light source, both to record the tomographic PIV data and for recording the interferograms that we use for measuring the deformation of the wall. The idea of combining the 2 systems was conceived by a smart graduate student. I had the intention originally an intention of using 2 different lasers with 2 different colors, but thanks God for smart graduate students, that wasn't really necessary. So this is the optical setup, tomographic PIV plus Mach Zehnder interferometry. To give you an idea how an interferogram looks like, you can see it here. Here is an sample. This is the original interferogram. It's quite noisy. We worked a lot on enhancing the interferogram. The difference between the top one and the bottom one is about 2 years of work of a graduate student that we developed correlation-based techniques to enhance the interferograms. to the level that we could actually determine directly the phase from the arc cosine of the signal. Here we did not need any subsequent filtering. But basically, when you have an object wave and a reference wave, you sum them together, you get the intensity distribution. The phase of the light appear like this. So you end up with this is the reference beam, this is the light object beam, the light propagating through the compliant wall. If you combine the two beams, you're going to get intensity of reference beam, object beam, and the cross term, which you're interested in, that has several terms. Several of them are constant. KCX is an intentional fringe pattern line that we impose by tilting one of the beams. And delta is really the term that we are interested in, that includes it's proportional to the difference in refractive index between PDMS and the NAI solution, and also proportional to the deformation of the wall. And this is really the term that we are after. The original interferograms look like this. I mentioned to you before that to clean them up because they were too noisy, we use autocorrelation of the signal in a certain domain to clean the signal, and then we cross-correlate and with the original signal with autocorrelation to reproduce the original fringe pattern. We also match, we restrict the distance in perpendicular to direction of the fringes in order to account to prevent negative effects from curvature of the fringes, etc., etc., etc. There is a paper in 2015 that summarizes all the calibration techniques, etc. The bottom line is that we start with interference pattern that looks like this. This is the raw data, and you can see that the fringes are actually undulating and meandering. And this is the final product that we analyze. I wonder how long you'll be able to sit and look at it before you go crazy, because those things drive you crazy. But anyway, once you calculate the phase distribution, this is the data. This is the wall deformation. Notice, by the way, that what you see right now is the peak to peak here is in order of a micron, okay? Now, the wall unit in this particular case is about 10 micron in this particular example. So the deformations that you actually see are only tenths of a wall unit. In many cases, they're even smaller, but they already modified the flow significantly. And that puzzled me until we learned something, and I'm going to describe it. Anyway, if you have the three-dimensional velocity field, we want to calculate the pressure distribution. You have two ways of doing it. You can use the pressure Poisson equation that anybody in the CFD business will use on a regular basis. In experimental data, we obviously have also experimental errors, and we need to account for them. So we opted to actually go ahead and calculate the distribution of material acceleration, and integrate the material acceleration spatially to get the pressure. For some reason, my slides move by themselves. Anyway, very near the wall, we also account for the viscous terms. Otherwise, we just integrate the material acceleration. We have published several papers where they talk about the uncertainty analysis in the measurements and associated issues related to it. The last versions is Wang et al. In Experiments of Fluid 2019, or an Agarwal et al. In 2021 in Experiments of Fluids. Applications of these techniques for measuring pressure, you can see it in GFM for turbulent shear layers in 2023. Recently, we also started playing with neural networks, and we compared the pressure calculation based on integration of acceleration to applications of neural networks. For when you have sufficiently dense particle distribution, the difference between the predictions are very small. When the particle distribution becomes very sparse, sparse means, let's say, 4 or 5 whole units apart, then at that stage, the machine learning tools, the neural network tools already give you better answers in terms of accuracy. This is, you can see it in experiments of fluid in 2000, last year, where the application of neural network. Most of the data I'm going to show you today is involved integration of acceleration. The raw data that you get from tomographic PRV looks like this. The bottom line, the bottom picture is actually the particle tracks for a turbulent shear layer. The top sample is really the particle tracks for the boundary layer. We usually actually calculate the acceleration of individual particles from their trajectories, and then you have an unstructured distribution of material acceleration. To actually integrate it, we convert the data to a regular grid using a constraint cost minimization method. Experiments of Fluid 2021 has the details, but basically is that you project from a group of particles surrounding a grid point, you project them into the central point in any grid spacing, while imposing all kinds of constraints. For example, we force the velocity fields to be divergence free. We force the acceleration field to be curl free, which basically means that we are forcing the flow to satisfy the continuity equation and the vorticity transport equation, while interpolating the data onto a regular grid by minimizing the error, minimizing from the original point, minimizing from prior steps, and then the physics-based constraint. So this is not just simply integration of material acceleration. We actually force the flow to satisfy the continuity and the momentum equation. So this is the pressure measurement technique. Now to calculate, this is the acceleration. If we want to calculate the pressure, again, I mentioned to you before, we have experimental error. To minimize the effect of experimental error, we developed what we call is an omnidirectional integration method, where we create a sphere around the sample volume, and the pressure at every point is a result of spatial integration from all possible directions. This way, we prevent errors from propagating, because if you have an error at a certain point, it keeps on propagating beyond that point. But if you integrate it to every point from all directions, you minimize this effect. Secondly, we also calculated the local errors, and in cases where we find large errors in material acceleration, we avoid these points. So we eliminate points where you have large errors in acceleration, and then we integrate from all directions to prevent, minimize at least, the error propagation to the measurement point, and we do it to every point. This is actually in early years, we started using it in 2D, and then we went to 3 dimensions. 3-dimensional calculation time became an issue, and as a result of it, we wrote GPU-based codes that can calculate the pressure. So it takes right now about 10 seconds to calculate the pressure distribution based on one 3D realization of the flow field. It is about 200 times faster than calculations based on the CPU of a machine. So GPU made a big difference in terms of how fast we can calculate the pressure. So now I have the pressure, and a 3-dimensional pressure distribution, and we have the wall deformation, and we want to see what we get. So give you some idea how kind of look like, how things look like. Notice in here we have the deformation of the wall. Notice the scales are not the same. It's not to scale. So the deformations that you see in the bottom are in the order of a tenth of a wall unit. And the pressure distributions are obviously cover substantial fraction of the boundary layer. But if you pay attention to a peak here, notice that there is a pressure wave that propagates with it and kind of is attached to it. So if you, and I've noticed that when I started looking at the data, that we see flow phenomena that expands to several hundred wall units that latch into deformations, and deformations that are extremely small and travel with it. And I know that it is caused by the deformations and not by the flow affecting the deformation, because the characteristic wavelengths of this deformation is a property of the solid wall. I will elaborate on it later. Now, if you look on the right-hand side, it's again the same thing. You can say pressure maxima latching to dimples in the flow, pressure minima latching to bumps in the flow, and they travel together. And the height to which the flow phenomena travel together with the deformation extends to hundreds of wall units. And that surprised me. Now, these are two examples. At the 6700 at Reynolds Tau, you can already see that the height of deformations are in the order of a 1 wall unit. On the left side, the 3300 is tenths of a wall unit. In both cases, the flow latches to the deformations and travels with it. And that's surprising, because if it was a rough wall with this roughness height, we would have said that that's a smooth wall, right? Tenths of a wall unit surface pattern. But it's not a stationary pattern, it's a moving pattern, it's a surface wave, it has a regular pattern. It actually is a wave, and that makes a difference, and we will discuss it further. Now, what happens to the mean velocity profile? I show you on the top, I show you result of boundary layer measurements, 2D PRV measurements in this particular case, and using single pixel correlation, so we can get a spatial resolution of better than a wall unit. The top row is results for stiff wall. The bottom row is results for compliant wall, exactly in the same location in the water tunnel. I wanted to account for all the inflow conditions and everything else, the tripping of the boundary layers, anything else that could actually affect the flow. If you look at the velocity of 1.2 meters per second, the characteristic height of the deformation is only half a micron. This is the RMS. Actually, this is the maximum deformation, only half a micron. Wall unit in this particular case, it's 20 microns. So these are really negligible levels of deformation. But you already see the beginning of loss of momentum in the inner part of the boundary layer. You don't have any more u plus equal y plus near the wall. There is a clear change. By the time you go to a deformation, to a higher Reynolds number, when delta nu is 9 micron, the maximum deformation in this particular case is 6 micron. So it's less than a wall unit, the maximum deformation, but you already see substantial momentum deficit. Even if you go to higher, in this particular case, you already have deformation when the maximum deformation is about almost 4 times the wall unit. You see, so this would be also a so-called beginning of a rough wall. You already see a substantial momentum deficit. As a matter of fact, all the viscous sublayer and big part of the buffer layer are gone. There is also loss of momentum in the log layer. So the compliant wall causes modification to the boundary layer structure, even for very small deformation heights. An important parameter also here is this E over rho U square. E is the Young modulus of the material, rho U square is the dynamic head of the flow. So this is the parameter that kind of, if I compared our results to those of numerical simulations, this is the results where things made sense and agreed with each other. As a matter of fact, here you can see a comparison. In the middle, these are results of DNS by Rosti and Brand, JFM 2017. On the left side, you can see our experimental data and for the compliant wall deformation for various values of E over rho U square. For the case of E over rho U square, now the DNS, it's at a very low Reynolds number. It's Reynolds number of less than 200. So there's a big difference in the Reynolds number, but at least for the dash lines and for the pink line, or at least for the dash line, the E over rho U square is actually, if you want, a dimensional parameter relating the material properties to the dynamic head of the flow, are matched with the experiment. So in experiments is 2.39, in the simulation 2.92. And if you look at the dash lines, you can see that the two velocity profiles are actually matched with each other quite well. So that really means that this is really the right parameter that you should use in order to compare and to characterize or non-dimensionalize the flow features. But anyway, the compliant wall is not a rough wall boundary layer. There's a clearly difference in trends. And but there is all the people that have done recently measurements of simulations clearly show a loss of momentum in the viscous sublayer and a buffer layer. So the inner part of the boundary layer is substantially modified, even for deformations that are extremely small. Now let's go and try to understand what happens. There's a classical paper performed by Chase in 1991. I'm trying to go back. In 1991, he solved the Helmholtz equation for the compliant material and excited it at different harmonics. So he excitated with P naught, some exponent of a wave, or tau naught, or shear excitation. Shear excitation also of a wave with a given wave number and frequency. What you see on the right-hand side is a wave number, horizontal axis, frequency, vertical axis. So this is a wave number frequency spectrum of uniform excitation of the material and how the plate will respond by solving Helmholtz equation for a viscoelastic material. You can see that there is a peak response of the material at a wave number that corresponds to 3 times the thickness of the compliant material. At all frequencies, there is a peak response at 3 times, a predicted peak response at 3 times the material thickness. By the way, this location involves flow speed equal to the shear speed or excitation frequency matched with the shear speed of the material, but below here your frequency is lower than if you're in this region, your velocity is lower than the shear speed of the material. Yet there is a peak response and 3 times the material thickness. Now let's look at our wave number frequency spectra that we got, first of all, for the deformation. So again, remember a horizontal axis, wave number, vertical axis, frequency. You can see that there is a clear advection at a certain speed. In our measurements, that speed corresponds to about 53% of the free stream velocity. There is a milder peak at about 90%, but everything here is in log scale. So most of the energy is in this wave. So the primary lobe, if you want, is described here in the movie, in the video in the middle. The smaller waves are very low amplitude wave moving faster. You can see them on the right side. For the rest of the discussion, I will focus on the waves involve advection at a speed, in this particular case, of 53%. By the way, the speed varied between 53%, if you look at the literature, to about 80% of the free stream velocity, without any clear trend with material properties. This is a mystery to me. I still don't understand why. So here you have the advection speed, USW. This is the advection speed of the wave divided by the free stream velocity for a series of shear speeds. Or if you want, this is square root of the shear modulus over the density for the compliant material. If you see the values that vary over a broad range of numbers, 1.5 order of magnitude, in all cases, there is no clear trend. They vary between anywhere 50% to about 75% in this particular case. What I'm showing here is Carpenter et al. Here involves many cases that have shown all of this range. This is one of those things that I still don't have an explanation for you. The red line is experiments done in Delft. The orange is our own measurements is one material, a much stiffer material. The green one is material that correspond to the current material. And then we present measurements, values varies. We don't know right now what affects the speed, but the speed does not correspond to the shear speed. And it's always a fraction more than 50% of the flow velocity. This is something we still need to explain. Now, if we perform conditional analysis and we look how does the flow structure look like near a bump, let's say that we put a condition of a bump on a surface, or we put a condition of a dimple on a surface. In both cases, we actually get a similar flow phenomenon where you have a spanwise vortex. It's actually a three-dimensional structure, but the preferred structure is a spanwise vortex that has a center at a certain distance, several tenths of wall units away from the wall. I'll explain the origin of it in a minute. And the pressure, there is a pressure minimum under the vortex, and that pressure minimum is what actually generates the bump. The flow induced by this vortex actually already creates a sweeping motion. That sweeping motion impinges on the surface, and the impingement on the surface is what creates a dimple. So the bump and the dimple are part of a wave pattern. They are moving together, they are advected together, and they always travel together. The dimple, notice the distance, the characteristic wavelength is almost 3 times the thickness. And if you remember the theoretical analysis, I mentioned before that the theoretical analysis also predicts based on material properties that it should be 3 times the material thickness. So the characteristic wavelength is dictated by the material. Anyway, this is the type of flow pattern that we see that is responsible. I should say, however, that the flow is three-dimensional. What you see here is a 2D projection. There is actually a converging flow from both out of plane ends towards the center of the vortex. So the flow contracts laterally near the bump, and then when it impinges on the surface, you have splatting flow that splits outward in both directions. Now, when you look at the flow, it makes sense, but if you look at the pressure deformation correlations, that's what you see here right now. You can clearly see, so you have here on the right side, you have condition pressure deformation correlations with a bump at 0. On the right side, you have a dimple at 0. In both cases, we get a negative peak, very high correlation in the order of 80%. It doesn't happen usually in fluid mechanics when you get such high correlations in turbulent boundary layer, but we do. You get a very high negative correlation between pressure and deformation, As you expect, you have a low pressure above the bump, high pressure around above the dimple. They come together. You can clearly see the characteristic wave pattern associated with the flow that actually locks in with the wall deformation, and they all travel together. And then the characteristic wavelength is in the order of 3 times the material thickness. So this is the pressure deformation correlations. This is the top view. I mean, I can spend half an hour on it, so I'll skip it. But if you look at the top view, when you look at you have in this particular case a bump, you can see an inward flow. So it's not only a spanwise vortex in here. You also have inward flow above the bump and a outward flow above the dimple. We have looked at it in several ways. We have done also conditional averaging as opposed to correlations. You get pretty much the same answer. So we know that this is really the characteristic pattern. Now, I'm still trying to understand, however, what is the significance of this height? Why do we get maximum correlation with the pressure at a certain elevation away from the wall? All of these things will become clear shortly. First of all, let's look at the magnitude of the deformation. This graph, horizontal axis is E over rho U square, is again the dimensionless, if you want, Young modulus of the material. And this is the RMS of the deformation. You can see results that measurements that we perform in 2 studies. You can clearly see that if E over rho U square is 60 or actually above 20, the amplitude of deformation in micron is extremely small. If you, by the way, on the left side, you have RMS. On the right side, you have the peak values for comparison. But once you go below 5, you start to see substantial increase in amplitude of deformation. And you already have cases where you will expect to see modifications to the boundary layer. You would not expect modifications when the deformation, RMS of the deformation is in the order of less than 1/10 of a wall unit. But as I mentioned before, even from the mean velocity profile, that happens. So first of all, what is the relationship between the RMS of the deformation and the pressure field? In here, we took the same data. On the top axis, I mean, in both cases, the horizontal axis is the RMS pressure versus normalized by the shear modulus of the material, square root of rho CT square. So it's P over G, or if P over E with some constant. And a vertical axis, the top figure is D plus. So we normalize the deformation with the wall unit. We get the results that we got here, and the results, even our own results, are scattered. And if we compare to measurements performed recently in Holland by Westerwille's group, you can see that there is the results do not collapse. But if you take the same data and instead of and you normalize the RMS of the deformation with the thickness of the material, so you have the RMS. For some reason, my PowerPoint is jumping all the time. I have no idea why. The RMS over L naught. L naught is the thickness of the material. You get, so this is actually, if you want, the longitudinal strain. Yes, it's the deformation over the total thickness, so longitudinal strain. And the horizontal axis is P over the modulus. So basically, you have a classical stress-strain relationship. The pressure over the modulus is equal to the strain. Amazingly enough, the slope of this line is 0.98. So give it a couple of % experimental errors. We basically have a linear relationship between the RMS of the deformation and the pressure RMS. So we have a very simple relationship between the RMS over the thickness. That's the only length scale that makes sense. Of course, it's true, by the way, only for shallow thickness, but D over RMS over L naught is just some constant times PRMS over the Young modulus of the material. So after so much effort, we got a linear stress-strain relationship that we learned in the first course in solid mechanics, right? When you compress an elastic material. So it's amazing that the pressure fluctuations give us such a nice correlation between the deformation. Now, the results, by the way, here, this is 3.5 orders of magnitude of deformation versus L naught. So this is substantial range of data. This is also substantial range of PRMS of over the modulus. These are some of the results have different thicknesses. So all of the data, because including our data in here, which are these are our own measurements with a thicker wall, all of the results collapse into a single line. So we know the relationship between PRMS and the wall deformation. Now the question is, why do we get that phase locking? And that thing bothered me because I'm reminding you, if you look at it, you can see how the pressure wave, I'm just showing you a plane of pressure. I mean, we have it in 3D, but I'm showing you a plane that coincides with the maximum deformation. And you can see that they are traveling together. And we are trying to understand why, what makes deformations. Look at D over delta nu, it's less than 0.1. Why does it travel together? Because if it was a rough wall, the flow would have been pretty much oblivious to it. So in order to try to understand it, I started searching the literature, and that was a good idea because oceanographers have been dealing with the similar type of phenomena for a long time. There's a classical papers by Miles followed by Lighthill's paper, in which they introduced the concept of a critical layer. If you have a wave on the surface moving, there is also a flow layer in the flow where the flow velocity is equal to the wave speed. For the fluid in that elevation, the fluid is moving with the wave. It's moving with the wave. At lower elevation, relative to the wave, the fluid is actually moving backwards. Above it is moving downstream. Lighthill already noticed, and it kind of makes sense, is that the highest correlations between the deformation, in that particular case was the surface waves in the ocean, and the atmospheric boundary layer above it, the highest correlations occur at the critical height. But in oceanography, that critical height is quite low, but not for the compliant wall, and I will show you in a minute. But you have a layer where the fluid, unfortunately, where the fluid is moving at the same speed as the wave crest. So you can, not accounting for turbulence, you have a fluid element that is moving with the crest. And we will see that this is actually the fluid element that is most highly correlated with the presence of the crest. And as a result of it, because any other element will see different flows and different wave height, this fluid element will always see the same height. And because of that, you end up with very strong correlation between the wave surface and the flow at that elevation. This is what happens in surface waves. Let's see what happens in our compliant wall. So I'm showing you here wave number frequency spectra, but in this particular case, not of the deformation. This is this is EPP. This is the spectrum of the pressure, vertical velocity fluctuations, horizontal velocity fluctuations. And the top row, I'm showing you an elevation where the high, I'm at elevation located here between the critical layer and the wall. So y is smaller than the critical layer, smaller than yc. In this particular case, if you look at the advection speed of vertical velocity fluctuations and the pressure, you can see that both of them are moving with the wave. They are not moving advected the local velocity. They are advected with the wave. If you go to an elevation which is higher than that of the critical layer, you see that the fluid element, I mean the turbulence, the eddies, etc., the eddies are advected with the local velocity. So below the critical height, and it doesn't matter what elevation you are, the entire turbulence is actually moving together with the wave, not with the local mean velocity. When you look at horizontal velocity, you see mixed trends. Vertical velocity fluctuations below the critical height, you have advection at the wave speed. Above the critical height, the advection is at the local velocity. So let's go ahead and find out what happens with elevation. So here I'm showing you the horizontal axis is y over the critical height. So the critical height is at this elevation. And the vertical axis is the advection speed of a disturbance of a fluctuating phenomenon versus the free stream velocity. So you can see that up to the critical height, the advection speed, this is advection speed of pressure disturbances. This is advection speed of the vertical velocity fluctuations. You can see that everything combined is advected at the same speed as the wave. So all the flow phenomena, all the eddies, we saw it visually also, are advected all the way to the critical height. They are advected at the speed of the wave. Above the wave, above the critical height, the pressure and the vertical velocity fluctuations are now advected at the local velocity. Below it, at the critical, at the advection speed of the wave. Now, if you want to see the coherence, we actually look at the coherence spectra. This is the coherence spectra at y smaller than the critical height. You can see, first of all, so this is a coherence, this is the coherence spectrum. Again, this is wave number, this is frequency. You can see that you have pure advection at y smaller than the critical height. You can see that the entire flow phenomenon is advected at the wave speed. At higher elevation, the coherence is lost, disappears, and also migrates, no longer matches it. Now, if you want to see the plots of the coherence, for example, and this is the coherence between the pressure and the deformation. So this is how the pressure, so this is the pressure deformation, cross spectra, normalized. You can see that the peak of the coherence between pressure and deformation occurs at the critical height, where the flow speed is equal to the wave speed. Below it, although the coherence is lower, it's still very high. Above it, it decays very rapidly. If you look at the correlations between pressure and deformation, you can see that the extent of the domain where the correlation is high goes a little bit higher than the critical height. But no matter what, the entire flow domain below the critical layer, the entire turbulence is advected with the wave, even when the wave is extremely small. Now, what you see results here is results for 3 different Reynolds number, the 3300, where the deformation height is only in the less than 10% of the wall unit, to 8900, where deformation height is already several wall units. In all cases, it's the same. The flow is all the turbulence up to the critical height is advected with the wave. So the correct length scale to understand how the turbulence is coupled with the wave is not the height of the wave, but the critical height, the elevation where the flow speed is equal to the wave speed. If you actually look at turbulent boundary layer and you try to compare it, say what happens in a typical turbulent boundary layer. So we collected data from simulations by Kim in 1983, and also we went by ourselves to the Johns Hopkins turbulence database, and we looked at advection speed of disturbances. We find out that the near wall, we are talking about y plus, this is y plus of 1, this is y plus in the order of 15. At y plus smaller than 15, the flow speed, the disturbances are propagating at the speed of the disturbance at the kind of in the buffer layer. Below it, actually, the flow is quite laminar. So, you end up with eddies when the beginning of significant eddies. So you can see the disturbances are traveling pretty much at the speed of eddies that are at elevation of about y plus 10 to 15. Above it, you have advection at the local flow speed. In our cases, the advection is all the way to the critical height. Now, the critical height already goes to, and then we look at the elevations. At the lowest Reynolds number, the critical height is in the order of, you see, the critical height is in the order of 60. If you go to the higher Reynolds number, the critical height is already in the order of 200. So all the disturbances, all the turbulence, all the way to at a Reynolds number of, let's say, 8900, everything below that height is advected with the wave. And this is amazing because you have very strong disturbances, but you have a certain elevation when the flow speed is equal to the wave speed. And in the space between them, in this particular case, it's about 200 wall units. All the turbulence is advected together with the wave, is latched into it and runs with it. I find it to be amazing and totally surprising. Again, as for comparison, for rigid wall, you can see the elevation of the dominant near wall eddies. In all the cases where we have a compliant wall, in this particular case, for example, at 3300, the deformation height is only less than a tenth of a wall unit, but anything below a y plus of about 60, 60 something, is moving together with the wall deformation. So where this is a case where we learned a lot from what oceanographers knew a long time ago, and for turbulent boundary layer, the dominant length scale is the critical height. Now, I'm going back to the graph that I've shown you before to show you to what extent the critical layer affects and dominates the turbulence. Here are the three Reynolds numbers. You can see that in both the two other two cases where delta, the deformation height is a wall unit of several wall units, we go deep into the log layer, and we still, so every turbulent eddy, not every, a majority of the turbulent eddies at height below the critical height are advected with the deformation. You can clearly see the results scaled on the right side. So we learned something new about compliant wall boundary layer. And that is kind of the final conclusion of my presentation. And I'm out of time also, so I'm going to stop here. And thank you for listening to me.
Thank you so much. It was very interesting, and I think we all lost track of time because we were really enjoying the presentation. If anyone has questions from the audience, please feel free to either speak up or type in the chat box.
I'm disturbing people's lunch, so.
How's it there?
Yes, yes, we can hear you, Tony.
Hi. Yes, thanks very much, Joseph. You have an extremely interesting presentation. I'm just wondering, can you just clarify that these under turbulent boundary layers, actually these compliant walls can show instabilities, and they can show divergence type instabilities. They can show traveling wave type instabilities. The sort of wave that you're showing is more associated, the faster wave, associated with traveling wave flutter. And I'm sure you know that Mohammed Gad al-Haq and his co-workers, did experiments on this. But I'm guessing, I'm assuming that your stiffnesses, the wall stiffnesses, are substantially higher than the ones that Mohammed was using.
The wall stiffness that we are using is substantially higher than what Mohammed was using.
Yes.
By the way, even the wall stiffness we are using right now is not stiff enough for what the Navy is interested in. So, yes. Yes, it is substantially harder.
Okay.
So the result in this particular case, for example, if you see the linear relationship between pressure and strain, pressure stress-strain relationship, Mohammed Gad al-Haq would not have got it because of the divergence wave, etc., etc. He wouldn't have got that. Was a nonlinear response. Here it's just we have a pure linear relationship between pressure fluctuations and deformation.
Yeah. No, I see that. Actually, could I also, sorry, if it's okay, as it. So there were some experiments done by Qingso Choi and the Russian group from Novosibirsk, Boris Semenov and his co-workers. I think in 1994, they did some experiments in Newcastle upon Tyne in England, and they had a very stiff compliant wall and under turbulent boundary layers in a water channel, and they actually showed drag reduction between 5 and 6%. Can you comment on that, Joseph?
Yeah, hot wire measurements performed in the 1990s. If you're going to tell me that the results were accurate to within a couple of percent, I question it. There was, yes, they claimed the reduction in Reynolds shear stress near the wall. Whether they actually saw a reduction in drag, I'm questioning it. Remember also that if you have wall deformations, you have to account also for the foam drag because you have effect of the pressure. So what they did is they measured the Reynolds stresses.
Yes.
And using techniques that were the best in the 1990s.
Okay, thank you.
So I mean, I'm not trying to criticize it, but
No.
I wouldn't have been able to do better at that time. Yes. So.
Sorry to hog this.
By the way, I should say we substantially increased the turbulence level. Okay.
Yeah.
I ran out of time, but Reynolds stresses are substantially higher than what you will see.
Right. Yeah. And so you get drag increase.
Yeah.
So, just one last question is about. I mean, this is a typical sort of viscoelastic material with a water flow. Actually, the density it's 880, I think, your wall, as compared with 1,000. Now, what happens if you don't have matched densities? I mean, the actual wall wave is going to be substantially different because there's inertia difference.
So this is why I value the fact that the numerical simulations, both by Rosti Brown and by Tamazaki, my colleague, show very similar trends in a totally different Reynolds number. You see the same momentum deficit, you see the same increase in turbulence, you see the same type of interactions with the flow. And once we started realizing that that's the critical layer, amazingly, everything matches. Yes.
Okay. Thank you.
So I mean, these are questions I ask myself too, as well. Yes.
Thank you, Tony. Peter, you like to ask your question?
Yeah, what was the compliant surface dimensions in the streamwise directions and I guess span-wise? It makes me think of scenarios in the laboratory or when conducting experiments.
In this particular case, the entire bottom of the water tunnel was a compliant wall. And the measurements, we also made some measurements so it's the entire boundary layer. So the test section is 85 centimeter long and 16 centimeter wide. Okay, so this and the entire surface is a compliant surface.
Okay.
So we molded. Go ahead.
I'm just thinking about scenarios where there's vibrations in a facility, or if you've got a model and it's simply supported and there's vibrations, would these vibrations typically greater than, you know, a few wall units, would they have a similar effect to what you're seeing in compliant surfaces?
First of all, I don't believe so, but the first set of measurements that I've shown only a couple of data points, we actually made those in an acrylic channel, and that acrylic channel was dancing, you know, because once we started seeing the deformations, we also started, you know, when you start making submicron measurements, you start discovering all of those things about your facilities you don't want to know. And this is why we went and built that water tunnel and went to a much more rigid wall. I mean, this is a massive steel structure. So in both cases, you see the same pattern. The wavelength, as I mentioned to you before, the wavelength of the deformation is 3 times the thickness. So the characteristic wavelength is directly imposed by the thickness of the material. So when we made measurements with a material that is twice as thick, the wavelength was twice as long. Okay, so we know it's everything matches with the thickness. And it's when, you know, if you do theoretical analysis and you get results that agree with what you get in a turbulent flow, we usually say that something is wrong, yes, because usually nothing agrees. But the predictions of the model are in terms of response of the material. That's 3 times the thickness. And again, the numerical simulations show exactly the same pattern. We have also played, by the way, with materials that have, you know, 2 different, for now, 2 different Young modulus and loss modulus, and we get exactly the same trend. That the wavelength is not affected at all by the thickness of the material. The wavelength is only affected by the thickness of the compliant layer. By the way, that has some limit, yes, because if you have very thick compliant surface, I'm assuming that eventually, like in deep ocean waves, you start losing that effect. But these are actually shallow compliant surfaces, clearly 3 times the thickness. So that's not facility. This is the properties of the compliant surface.
Thank you. We have some questions in the chat. So Aditya has asked, can you please comment on an active compliance or deformation scenario? Do you expect some of these observations to hold?
First of all, if you have active compliance, that really means that you no longer have a regular wave, that you manipulate it, etc. Then it'll be dangerous for me to make any predictions, because in here you have regular. I mean, we have homogeneous surface. In a minute you alter the homogeneity of the surface, things change. and then we are just at the beginning of starting to play with inhomogeneous materials. I just ran out of time. You start, because you have inhomogeneous materials like surface wave, you start seeing refractions, of surface waves. You also have, by the way, at very low speed, lateral, you have wave propagation in a lateral direction. A lot of other things will happen, yes. So it's hard to guess, but I can tell you that you can manipulate the waves using an active means. Yes.
Thank you. One more question from Kevin. When were the wrinkles first generated, and will they grow similar to waves, for example? Not sure.
I am not. You see, the only mystery, big mystery to me, is that I mentioned before, I don't have the slightest idea what controls the wave speed. I know what controls the wavelength. I don't know what controls the wave speed. When I went from a channel flow, that vibrating channel where I had advection speed of 72%, to this rigid water tunnel, the advection speed changed to 50% and 60%, depending on cases. I don't even understand that. So you have, I'm assuming that you need, like wind waves, you will need a fetch, certain streamwise distance where the flow and the wave need to interact with each other to get such a high correlation between pressure and deformation. So if you have a very short streamwise distance, you may not get the same correlations. So, but I am not sure about what I'm saying right now.
Yes, thanks. And one last question from Kunalan. Can I assume that blood flow through an artery involves a compliant wall mechanism? This is very
absolutely.
Yeah, and they also have a question at the end. This is very important for understanding the deformation of tissues in the studies like this. I'm wondering, should we conduct a study involving circular walls?
This is the second time somebody asked me this question, and the first time I heard about it, and now the second time, by all means, I think it's really a nice motivation to try to see what really happens when you have axisymmetric boundary conditions, and try to figure out whether it has an impact on the deformation of the wall, have an impact on the flow and how to interact with each other. Remember, blood flow, many times is slow Reynolds number. So if it's not a turbulent flow, things are different. But if you get a high enough Reynolds number, you might, like in IOTA, etc. Yes, the formations might play a role. By the way, arteries are deformable. You actually use for pumping.
Yes, Tony, you want to add something? You're on mute.
Can't hear you.
Oh yeah, sorry. Thanks for your answer. Just a further comment on that question. The other difference is, of course, in blood flow, it's pulsatile, so that creates quite a difference. You can get inflection points in terms of the velocity profile. And the other thing, it's maybe that
you're absolutely correct. Yes.
The other question, there are some work on the circular, actually symmetric, done by Kumaran and Shankar in India. They've done some work on that problem. So whoever answers the question, look up Kumaran and Shankar.
Okay, I will. Well, thank you.
Yeah.
Thank you. Do we have any other questions? It's not. So thank you again. We held you up late at night, so I think we'll just end this here. But
it's enjoyable. Thank you very much. Thanks for inviting me.
Thank you for the great talk.
Bye-bye.